Now, I have given you lots of algorithms, TD learning, Q learning, this, that. None of them work in practice. Absolutely none of them work in practice. In practice is an important word. Why do they not learn? See, if you go back, and this you should have been asking me, not me reminding you that you should ask me. When we started doing search, we said that the search space is usually extremely large. It is so large that we can't even represent it in the memory, we can't even run a Dijkstra's algorithm, which is why even shortest path computation we do using A star and whatnot, where we are expanding only a small number of states. But then when I came to uncertainty, I said there is a state space, there is an action space, there is a policy that is a mapping from states to actions, I am always maintaining the state space. You should ask me, how can I do this? State space, isn't state space too large? And the answer is it too large? Absolutely it is too large. It is always going to be in practice they will have some features in your problem, and then your state space will become exponential in that feature space. So, all this business about memorizing a policy, doing value iteration, doing Q learning, these are good for the books, but they do not work. And the reason they do not work is because in realistic situations we cannot possibly learn about every single state, just not going to happen. Too many states to visit them in training, too many states to hold the Q table in memory. So, what do we do? Now, let us look at the state of the class. The state of the class is where Vaibhav is sitting on chair A5 and Shayan is sitting on chair B19 and Parth is sitting on chair C16, etc., etc. And I am standing in front of this dais. This is my state of the class. Some people are absent, of course. Does that mean I should teach you differently? No. Right? If tomorrow Shayan decides to not come or come and sit in chair A15, should I teach you differently? No. It is possible that I can't make some jokes because I have to make jokes on specific people and that person is no longer in the class. So, I might make small changes in my narrative. It is possible that there is some big event happening because of Facebook and nobody shows up in my class. Then do I teach differently? Yes. Maybe only 4 people show up. Maybe I will say let us skip today's class because more people will suffer if I teach today. So, I will decide what to do based on you and us, the state of our class. And suppose my throat is bad, I just can't speak, no voice is coming out of my mouth. Will I teach differently? Yes, I might not teach, I might show you a video, I might say no class today. So, some features are more important than other features. My ability to speak, my physical presence in the class is unfortunately more important than yours, right. But individual small changes in the state do not really matter very much. Some things like where you are sitting completely does not matter. Some things regarding how many of you are present do matter a little bit. So, actually I do not need to train myself doing many classes again and again and again with each of you sitting differently and trying to teach again and seeing what is the reward. That is just too much to expect. If I have to learn the value of every action in every state independent of the other state, I am making a fool of myself. There is too many states, too many actions, infinite samples of SA pairs do not make sense in practice. So, what do I need to do? What do I need to do? You want to generalize. Imagine you do training with some classes. Let us say I taught one COL333 class, I taught another COL333 class. Let us say I taught this a couple of times. Now, the third time I teach, I have sort of figured out how do I teach, what works better, what works worse. It will still keep improving, I will still continue to learn, but the specific features of the state, not all of them may be important. So, I need to say that this state is very similar to that state. So, the action that I take in this state should be very similar to the action that I take in that state, or that this state is very similar to these 2, 3, 4 states, and the action that I take in this state should be very similar to the actions and an aggregate of that of what I take in those states, and so on and so forth. So, I need to generalize my experience. In fact, in real world, in real life, I never get the same state twice. Why? Because time is constantly moving. So, if you include time in the state space, I will never get the same state twice. But for many problems like taking an exam, the actual time does not matter, only the relative time matters. So, I need to generalize experience to new similar situations. This is the fundamental idea of machine learning. In machine learning, I am usually given some training data and I have to learn a function to predict a particular thing, whatever, predict whether the image has a dog in it, predict whether the person uttered the word box in it, whatever, right, in the audio, whatever classification task you have. Is this email spam or not? So, we now need to say that in order to make any of this practical, let us do generalization. And how do we do generalization? Well, we use the same idea as we used in Minimax. So, we describe a state using a vector of features. Now, we can write the Q function, which is what we were writing as QSA separately, a separate parameter was being trained. Now, we will hypothesize that Q function has a specific functional form. That functional form is, let us say, a sum of basis function representation. The basis functions are features f1, f2, f3, fn, and each feature is more important or less important. So, each of them has a weight wi for the feature fi, and we take summation wi fi as the representation for q. Is this an approximation? Yes, and it also depends on how good your well, so there are two things, how good your weights are and how good your features are. And in the previous version of machine learning, who gave the weights? The machine. And who gave the features? The human. So, we had this division of labor. The human came up with some features, like on this chessboard, how many queens do I have, how many pawns do I have, how many pawns do I have very close to the queening move, how many, etc., etc. How many checks can I give in one step, how many checks whatever can I receive in one step, all of that are features, and a chess expert designs them. And something similar was happening in Go also. Some human expert will design those features. And then if your features are very good, then maybe you will be able to learn good weights, and that is a machine learning problem. The machine will say, okay, give me a lot of games, give me the features, I will try to give you the best values of wi's. And it is possible that it will still be an approximation, because it is possible that Q function is actually not a linear function of fi's. So, that is also possible. But the advantage of this approach was that our experience was summed up in a few powerful numbers wi's. If my human designer gave 20 features, I have to learn 20 numbers, big deal. If they are smart to give me 100 features, well, I will still have to learn only 100 numbers, still big deal. See, if you think about the number of configurations in the game, they will be just more than the number of atoms in the world. But all of that data I am compressing in a few small features. So, that is not bad, let human designer come up with 1000 features, 100,000 features, it is still much better than the large state space we have to deal with, and humans can only come up with so many features. Right. Now, disadvantage is that states share features, but they actually will be may have a very different value. So, in fact, therefore, you can't do too much with this approximation, but we have to live with that. So, let us see how we used to do it in the previous world, and then I will talk about how we do it in the modern world. So, in the previous world, for exact Q learning, this used to be my equation. QSA is equal to QSA plus alpha times the estimated value minus the new value. Now, I am not maintaining QSA separately. In fact, let us say I have some WIs that I have already estimated. That means I can compute QSA and QS prime A prime by plugging in the actual feature values for SA and multiplying with the appropriate current weights and computing some value QI or QSA. So, again this is computed, this is computed, right. This is the difference that we have to maintain. What we do is, and what parameter do we have to change? We have to change the weight parameter, because those are my free parameters. My machine learning has to figure out the weights. So, what we do is that we say Wm, the mth weight for the mth feature is nothing but the previous value plus alpha times the difference multiplied by the feature value. So, this difference is the same as in the previous equation, except now it is computed as opposed to freely estimated, but we multiplied with the feature function. Now, why do we do this? Let us make sure that we agree with this. So, what happens? Let us say my value needs to increase, value of QSA needs to increase. Now, let us say the value of QSA needs to increase, then which weights need to increase? The weights which were positive in the weights for which the features were positive in SA, and which weights need to decrease? The weights for features which were negative in QSA. So, by multiplying this term with FM, I figure out the sign, the direction much better, because if FM is positive, this weight increases, if FM is negative, this weight decreases, which is what we wanted to do. But you can say, why did we multiply with FM? Why not square root of FM? Why not square of FM? Why not log of FM? Why FM? We agree. You can say we agree that my sign is right, the direction is right, but how do we figure out the magnitude? And there we need to use a little bit of theory. So, the theory is like this. It is a theory of optimization. The optimization is, and again I am taking using a different equation, different setting. Let us say I am x, I want to figure out the function f that finds y. Let us say I am given these observations in red, and let us say I hypothesize that y is equal to fx is a linear function. So, y is equal to mx plus c. Now, for a given set of m and c, I will make some predictions. I will have a linear line, and then I can figure out the error. What is the error? The error is what is the y that is estimated and what is the y that I should have predicted. That gives me the error. So, y hat is what I predict, y I is what I should have predicted. This is my target value and this is my predicted value. Y I is target, y I hat is predicted. Now, I say that I want to reduce this error irrespective of the direction, positive, negative. So, I just square it and sum it, and I say that I want to minimize the sum of the squared errors. This you can write down as y I minus summation k w k f k, right, because y hat is predicted by a sum of a linear function. So, therefore, when I minimize this error and let us say this is my error function y minus summation w k f k, I will take the derivative with respect to w, because those are my weights. So, I take the derivative with respect to w and I want to set it to 0. But what is the derivative? The derivative is nothing but y minus summation w k f k times f m x, because weight k is derivative with respect to weight j is 0 for j not equal to k. Okay? I am doing this algebra very fast, but I will do it slightly slower next week. So, therefore, what I find is that when I do w m plus alpha times the derivative, this becomes exactly the equation that I was interested in. This is the difference of the prediction, this is the current error multiplied by the feature value. So, in case of approximate q update, this is y, which is r plus gamma max a q s prime a prime, the target value, and this is the predicted value minus QSA, and this is the difference, and it gets multiplied by Fm of x. So, therefore, if I have a squared error as my objective function and I want to find the right weights, then my derivative is such that it multiplies the feature weight to give me the magnitude of the change. Okay? So, this is the underlying theory for why we have this particular equation here. Okay? So, last but not the least, linear function has some advantages and some disadvantages. It has some advantages in the sense that suppose my data is very noisy, then a linear function sort of removes the noise and gives me the best fit line. So, it will make a good prediction. Suppose my data was in fact linear and I just had experimental error, then I will compute the value of this point as somewhat reasonable. On the other hand, if I allowed it to fit a very general curve, then it may overfit. Overfit means that it will fit perfectly, but it will not generalize very well, because now for this point it may say it should be very high, this value, but there is no evidence that it should be so high. So, there is some benefit for having low capacity classifiers because they generalize better, but then they have low capacity, so they can't represent very much. Of course, linear approximation is not powerful enough in practice. You can't argue that all features are affecting linearly my final q value system. So, what do we do? And in the most modern world, we use deep learning. So, this is where deep learning significance start to come. You have feature values and you want to fit a new function y or QSA or whatever, and you do not want this function to be linear, you do not want this function to be low capacity, you are letting it be high capacity. You are allowing yourself to have lots of parameters. That is where deep learning comes into picture. So, let me summarize our topic for today, which was RL. RL is a very general problem, right. It is the problem where I have to take long term decisions in an environment where there is uncertainty and I do not even know transition and reward function. So, it is sort of most general single agent as long as it is not playing in any adversarial game. The main idea for all the other algorithms is expectation is average of samples. So, this is the technical core technical idea that you should keep at the back of your mind always in life. And then there were many interesting ideas like how we connect with people in terms of temporal difference and their happiness, how we connect with exploration exploitation trade offs and so on and so forth, right. So, agent learns as it gathers experience, agent learns as it optimizes its reward, it does some exploration exploitation trade off, but in actually making it work, you have to do some kind of function approximation where deep learning will come into the picture, and therefore, if we do deep learning for reinforcement learning, that field of AI is called deep reinforcement learning. And this is the rage today. RL was a very important community theoretically 5 years ago, but not a very important community practically. But in the last 5 years, after using deep learning, after all this AlphaGo success and so on and so forth, deep reinforcement learning and interest in it has skyrocketed. Lots of people are interested in it and lots of very exciting ideas are coming out of that particular community today. I should also point out that in the last set of lectures when we did Markov decision processes, I said that MDPs are used in lot of applications. But now I want to say that yes, MDPs are used, but not value iteration or policy iteration, not planning style MDPs. You rarely know transition function or reward function. For example, if you are trying to control cancer through radiation, you do not know the exact transition function of how much cancer tissue is going to burn and how much real good tissue is going to burn, how your body is going to react. You do not know the transition function. You can estimate it using reinforcement learning, but you do not know it explicitly. If you are doing forest fighting, you do not know exactly how you put how much water on the certain tree, how much fire will get extinguished. When you are working in a real setting, you almost never know the transition function of the reward function. Sometimes you use a training step, learn these and then use VIPI, which you can call model based RL, and sometimes you have it approximate and you let the model figure it out as it does better and better actions, and that is where you do more interesting reinforcement learning. When you play real games, this becomes even more important. You do not know with what probability Pac-Man will go left, you do not know with what probability Pac-Man will go right. Whatever interesting game you are playing, you do not know when the enemy is going to come and kill you from where. You do not have all that probability transition function. So, you learn it as you are playing the game. So, RL is a most important, one of the most important AI problems, and we have almost completely done this, except that now we will sub-goal on deep learning. Next 3 lectures we will talk of deep learning, and then we will talk about how it fits in the big picture of deep reinforcement learning. Okay? So, we will stop here.